Good afternoon, everyone. My name is Jingray. Today, I'll be presenting my FYP project that I work on under the guidance of my FYP supervisor, Prof. Cheng Eng Shao. I'll be going through the 6 main components shown on the screen with their respective slide numbers specified below for your easy reference. Now, what is the FAQ retrieval system? Businesses typically set up websites. When a user needs some information, they typically go through the FAQs of the website just like user A. However, businesses can also set up chatbot that will help users to navigate their web pages. Now, users can engage a chatbot like user B by sending a query to the chatbot, and the chatbot will find the most relevant answer from the FAQ web pages to answer the user query. Therefore, what is encapsulated in this blue box is the FAQ retrieval system. FAQ retrieval system can give users a better user experience that ultimately benefits the businesses in many ways. To set up FAQ retrieval system, artificial intelligence markup language (IMML) can be used by defining patterns similar to the one shown on the right-hand side. The system will answer the query by performing pattern matching. However, this approach requires a lot of manual work and labor costs to define accurate patterns. A model approach would be to use deep neural network model. Suppose that the user submit a query and there are n number of FAQ pairs. This approach will use a neural network model such as BERT to evaluate the similarity between the query and the first Q&A pair and continues until it reaches the last Q&A pair. Finally, the Q&A pair with the maximum similarity score is used to answer the user's query. This is also how the team at NTU SpeechLab has set up their chatbot based on the FAQs of MSF. As a result, the chatbot can be set up automatically in an end-to-end manner using only the FAQ dataset. While this approach is effective and provides cost savings, there are often insufficient FAQ pairs for model training. Therefore, we need to perform data augmentation, which is the focus of this project. Now, suppose we have the question and answer shown on the screen and we want to perform data augmentation manually. For every FAQ pair, you will generate paraphrase of the question while retaining the same answer. You may then come up with these paraphrases. However, you will have to repeat this process n times for n FAQ pairs. Each FAQ pair, you are generating k paraphrases of its question field. This implies that this process becomes increasingly manual intensive and expensive by a factor of k for every new FAQ pair that you get. While this way of data augmentation can be manual intensive and costly, it is undeniable that the paraphrases generated by relevant domain experts are likely to be high quality, reliable, and specific to the domain of the FAQ itself. In this project, we view paraphrases to be domain specific if the paraphrases retain domain terms that are abbreviated, such as Child Development Account (CDA). As a chatbot of NTU SpeechLab based on similarity evaluation was set up in an end-to-end and automatic manner, it was not an option to perform data augmentation manually. Doing so will introduce a manual element into an otherwise automatic process. Therefore, past FYP students have worked extensively on the task of paraphrase generation to perform automatic data augmentation, specifically through back translation or word replacement. However, the paraphrases generated from these two approaches have some known issues. I will illustrate this issue with concrete examples in the later literature review. Therefore, in this project, we hope to tackle the task of data augmentation by using pre-trained language models so that we can generate high-quality and domain-specific paradata autonomously. Effective augmentation of the FAQ datasets translates to savings on the cost of domain expertise to manually generate paraphrases and complements the end-to-end setup process of FAQ retrieval system that uses neural network model to perform similarity evaluation. There are three main ways of performing paraphrase generation as shown previously. The first way is the back translation, which can be achieved using statistics on neural network with neural network being more recently introduced as indicated by the blue timeline arrow. The second way is the word replacement, which can be tackled using various means as shown. Each of the listed means are described in greater details in my FYP report, but in my presentation, I will explain the gist of these two approaches using examples. The third way is using pre-trained language models, which can be approached using unsupervised or supervised learning. This is one of the latest ways in NLP to tackle paraphrase generation. The gist of back translation involves translating the original sentence from the source language to the pivot language and back to the source language. As I do not have an existing back translation system to produce the results, I have performed the translation using Google Translate to obtain the results shown on screen. Back translation can be an effective way of data augmentation, but it fails to generate domain-specific paraphrases as the same word can be expressed differently in different domains. One way to perform word replacement is to use contextualized word embeddings that takes into account the words surrounding the target word. Such use is implemented in the Python library NLP augmentation. If we perform the insert operation on the original sentence, we may get paraphrase 1. When we perform the substitute operation on the same original sentence, we may get paraphrase 2. From these two examples, we can observe that words of domain-specific terms can end up being replaced as shown in paraphrase 2, and paraphrases may also turn out grammatically unsound as shown in paraphrase 1. Language model works like a black box whereby we pass in the input question and get the paraphrase as the output. As paraphrase generation is random by nature, it is necessary to perform candidate selection to retain high-quality paraphrases. In my FYP report, I have described two recent works that tackle paraphrase generation in a supervised and unsupervised setting respectively. Our project closely relates to the work based on supervised learning, but improves on it by focusing on generating domain-specific paraphrases and generating paraphrases of questions instead of sentences. Our project also extends the work based on unsupervised learning, specifically in their candidate selection process, where paraphrases are filtered based solely on their semantic similarity with the original, which is not enough. This is the system architecture that I designed and implemented in this FYP, and with the following objectives. I will explain the components of the implemented system in the subsequent slides. To prepare the neural network model for the task of paraphrase generation, we downloaded a clean T5 model and fine-tuned the T5 model on a labeled paraphrase dataset released by Cora in 2017. This dataset gives us around 140,000 paraphrase pairs. Among all the labeled paraphrase dataset available online, I chose Cora question pair as my training dataset, primarily because it contains paraphrases of questions and not sentences. As the size of this fine-tuned T5 model was too large to be uploaded to my GitHub repository, I've implemented a feature where the system will automatically download the model from my Google Drive into the user's local drive. These features activates automatically when the user first uses the system and does not have my model saved locally. In the fine-tuning process of the T5 model, we experimented with the various values of the hyperparameters and finally settled upon the following values for the hyperparameters shown on the screen. After we have fine-tuned the T5 model, we are ready to pass in each of the FAQ questions one at a time to the model for paraphrase generation. Alongside with the FAQ question, we also need to pass in the generation arguments. I have set the following default values of the generation arguments. I find that these argument values gives me the most consistent results when I repeatedly perform data augmentation with my model. As the argument num return was set to 40, the T5 model will generate 40 paraphrases of the given original question. However, we may not want to keep all 40 paraphrases as they are unlikely to be equally good given the random nature of the generation. This makes the later candidate selection process necessary. Furthermore, we may also observe that domain-specific terms may end up getting replaced during the generation, which goes against the objective of our project. This leads us to our next slide on pre- and post-processing. To perform the pre-processing of the original question, we extracted the abbreviation CDA and its expansion, Child Development Account, and retained only the abbreviation CDA. Post-processing is then performed on the paraphrase generated by reinstating the abbreviation and its expansion. This form of processing is a novelty feature that helps us to ensure that domain-specific terms are retained without any parts being replaced by synonyms, while helping our model to generate paraphrases of all FAQ questions successfully. After we perform post-processing of the generated paraphrases, we decide which paraphrase to retain using the decision tree shown on the screen. This candidate selection consists of step 1 and step 2. I will start with explaining step 1. In step 1, we accept paraphrase P if it has a similarity score of at least 4.0 when compared to its original question Q2. The threshold similarity score of 4.0 was chosen so that we ensure that paraphrases are semantically similar to their original question while being slightly different from the original question. We will now look at a demonstration of step 1. For the demonstration of step 1, we use 3 original questions from the FAQ, where the first one is used to generate paraphrases with my fine-tuned model. These are the paraphrases generated by my T5 model. We will then load a clean expert model to determine the score between the original and its paraphrase. We will then carry out the step 1 by checking whether the similarity score is above 4.0. Paraphrase above 4.0 are accepted, while paraphrase below 4.0 are rejected. The paraphrases accepted in step 1 are passed to step 2. Step 2 is a novelty feature that I have incorporated into my candidate selection process to check whether paraphrase P is more similar to its original question Q2 as compared to other questions in the FAQ dataset. The primary inspiration for step 2 was because I observed that in the FAQ dataset, there are some very similar FAQ questions that are mapped to different answers. For example, the questions with class label 1 and the question with class label 2 are mapped to answer 1 and 2 respectively. But when we compute the similarity score between the two questions, we obtain a very high similarity score of 4.0. I have provided more examples of similar FAQ pairs in my FYP report. This observation explains why some paraphrases of question 2 turns out to be more similar to question 1 and hence are rejected in step 2. We will now look at the demonstration of step 2. For the demonstration of step 2, I will use paraphrase 1 and 2 as an example, and both paraphrases are generated from the original question shown above. This original question is from the FAQ dataset. Now, using the same expert model from step 1, we submit paraphrase 1 as a query and the FAQ dataset as a knowledge source to find the top 5 most similar questions from the FAQ dataset. As you can see, in this case, the position of the original question is second place. Therefore, position is 2. As the position is not 1, paraphrase 1 is rejected as it is not the most similar to its original. This process is repeated for paraphrase 2. As the original question is now in first place, position is 1. Paraphrase 2 is therefore accepted. The step 2 of candidate selection process is crucial in shortlisting eligible candidate paraphrase, as you may have observed by now that even though paraphrase 1 with a score of 4.61 is more similar to the original than paraphrase 2, paraphrase 1 is not eligible as it is more similar to other questions of the FAQ instead of its original. I have implemented the command line interface shown on the screen so that the user can use this interface to perform data augmentation of their FAQ corpus by specifying its location. I also allow users to decide how many M paraphrase to generate for each question, with the default being 40, and to retain the top K paraphrase during the candidate selection. If the user decided the K value to be 5, then the size of the FAQ dataset will increase by around 5 times. For my results, I've included some additional paraphrases that was generated by the system for the original question. How can I save in the child development account (CDA)? From paraphrase 1 and 2, we can observe that candidate selection is now more reliable with the step 2 that I designed, as we cannot depend solely on semantic score between the paraphrase and its original. From paraphrase 2 to paraphrase 5, paraphrases retain the domain term child development account in full, while they remain on topic and have varied grammatical structure. All in all, we have tackled the task of data augmentation of FAQ dataset using pre-trained language models such as T5 and expert model. Firstly, we put in efforts into training the T5 model with the optimal hyperparameter values and the most suitable labeled paraphrase dataset Quora question pair. Secondly, the abbreviation handling in pre- and post-processing that I designed also help us to retain domain terms within the paraphrases generated. Thirdly, we improved the candidate selection process with an additional step 2 that I designed to handle the observation where there are often similar FAQ pairs within the dataset. Lastly, we provided a command line interface that users can perform data augmentation of the FAQ dataset with the provision of a few input parameters. While we have done our best to design and implement this system with the limited resources we have, this project is by no means perfect and can be possibly improved in the future through these 4 ways. Firstly, we can improve the performance using new language models introduced in the future. An example is the recently introduced GPT-3. Secondly, we can use name entity recognition, in short NER, to retain domain-specific terms in a greater variety of formats such as organizational name and date. Thirdly, we can perform question type recognition in the candidate selection process to ensure that the prefaces retained have a wider variety of grammatical structure. Lastly, we can use actual user queries after deployment as an in-domain dataset for fine-tuning the neural model. Thank you everyone for your time and to Associate Prof. Cheng Eng Xiong and his team for their guidance and feedbacks. Thank you.